And actually, 2 weeks ago, I gave you a quiz to solve a dictator game with a full five, no, with a 5 possible offers. I'm going to explain that game. There are 2 players, dictator and recipient. Dictator was the first player, and the recipient was the second player. Dictator are dividing $4 with recipient. Dictator can choose between 0 to 4 as an offer to the recipient. For example, if dictator gives $1 to the recipient, then recipient will, if recipient accept that offer, then recipient will get $1, and dictator will take $3. So how can we draw a game tree? Think about it. Dictator has 5 options from 0 to 4. 1, 2, 3, 4, $0. At each node, because the dictator decides first to give that offer to the recipient, right? And the recipient, once that offer is given to the recipient, then recipient will choose between accept or reject that offer. Whenever the recipient rejects the offer, they will 0, 0 everywhere. However, if the recipient accepts that offer, then a player, they will get that distribution of that $4. So think about it. First, player one choose one offer from 0 to $4. That is the amount of the second player. Okay. Then at each node, second player will take that offer or reject that offer. Okay. Now look at this. So that is the game tree. Okay. Now think about it. Think about it. We are going to solve with backward induction. Right? So think about that. If this game node is reached, if player 2 accept that offer, then player 2 will get 4, but reject the offer, then player 2 will get 0. So the player 2 will accept that offer. That is reasonable. When this node is reached, then player 2 will accept the offer because 3 is better than 0. And also accept and accept, right? But the player 2, if the 0 is given offered to the player 2, it is indifferent between accepting or rejecting because 0 and 0. So there's no difference, right? So if I'm writing the possible action of player 2 will accept the offer if the offer is greater than 0. However, if it is 0, then it is indifferent between accepting and rejecting. Okay? So actually there are 2 strategies. One strategy is accepting every error. Another strategy that player 2 can take is to take an offer if that is positive, otherwise it is rejecting. There are 2 types of strategy. Now think about player 1. Okay? If player 1 Actually, player 1 does not have any incentive to give a positive offer. Maybe if player 1 gives $2 for the second player, I mean, it will get 2. However, if player 1 gives $1, and it will be accepted by the player 2, and the player 1 will get 3. So it's better than 2. Now, player 1 has two possibilities. If player 1 decreases to give $0 to the player 2, player 2 may take it or reject it. If player 2 rejects the offer, then player 1 has an incentive to give $1, a little more. However, once the player 2 decide to give $1 player 2, then player 1 all the time has an incentive to decrease its offer from $1 to $0 because if the player 2 is accepting, I mean, the pay-up that player 2 can get is $4, which is greater than $3. So that, I mean, they are circulating again and again and again if player 2 is rejecting. However, if player 2 is accepting, then this game will be over because player 1 is satisfied and there's no other way to increase one's payout more, and player 1 accept it. Even though player 2 decide to reject, still their payout is 0 and 0, no incentive. So that is a subgame perfect Nash equilibrium. Okay, so the SPE is player 1 gives 0 to player 2 and player 2 takes the offers everywhere. This is an SP. Again, what I'm arguing is that this is not an equilibrium. Player 1 gives, for example, 1 to player 2, right? Actually, there's one more SPE. Player 2 gives 1 to player 2, and player 2 takes the offer if the offer is greater than 0. And if the offer is 0, then the player 2 reject the offer. This is also SPE. There are two SPE. Think about it. This play is playing like this, accepting when it's positive. However, when it's 0, then player 2 is rejecting. Then the player 1 try to give 0 to the player 2, then that will get 0. So it has an incentive to increase 1. So, I mean, then player 1 can get 3 and player 2 can get 1. So this is 1 SPE. However, once this node is reached, maybe player 2 can take that offer because it's indifferent. I mean, emotionally, it gives you different emotions, but once this node is reached, in terms of the material payout, there's no difference between accepting and rejecting. So if the player 2 decide to accept once this node is reached, then this is also another equilibrium. I mean, player 1 gives 0, and player 2 take that offer everywhere, at every node. The other equilibrium is that player 1 gives 1 to 2, and player 2 takes everywhere. It is positive, but player 2 is rejecting once 0 is given to the player 2. So there are two equilibrium. there are two SPEs. However, I mean this is the result because the player 1 only can choose integer number from 0 to 4. However, if player 1 can take a real number in 0 to 4, what it means, player 1 can take every number in 0 to 4. So in that case, there are infinite number of branches here to represent a certain real number. In that case, the unique SPE is that player 1 gives 0 and player 2 takes all operas everywhere. I mean, again, the reason why we have two subgame perfect Nash equilibrium is because player 1 can take an integer number from 0 to 4. However, if I just twist the game a little bit, and player 1 can take every real number from 0 to 4, then, I mean, even though the player 2 has strategy like that, if that offer is positive, then player 2 takes it. If the offer is 0, then player 2 reject that offer. Maybe player 2 can take that kind of strategies. However, that cannot be SP in this situation. Because player 1, in that case, player 1 may try to give 0. Then player 2 is rejecting 0. Once the player 1 increase just a little bit on offer, then player 1 can get a positive payout because player 2 will take every positive offer. However, once that offer is accepted, then player 1 just try to lure an offer. By doing that, player 1 can increase its payout. There will be a positive small number which is smaller than the previous offer, but that is positive. So that is not an equilibrium at the end of the day. The only possible unique answer is that player 1 is taking that offer. I mean, player 1 gives 0 and player 2 takes every offers and everywhere. Then once that node is reached, even though player 2 is rejecting, still the payout of player 2 is the same, so no incentive to deviate. Okay, so think about it. If you finish understanding this game, and if you look at alternative offer game, you can understand a little more. Okay, I'm stopping here.